Unit 4 notes on chemical reactions. Now, this unit is going to be, or this topic is going to be over stoichiometry and all things involved with stoichiometry. All right. Now, please make sure you've got everything for this. You're also going to need, on top of everything else, you are going to need a calculator as well. So make sure you grab that. But otherwise, we're going to go ahead and get started. All right. So for stoichiometry, again, remember that stoichiometry is essentially our method for converting from one substance to another. So it's essentially a very, very important topic in chemistry because a lot of times we're not talking about the specific element in this. We're actually going to be looking at elements as a whole, elements in a chemical reaction, and we're trying to find out what the results would be. Okay, so let's take a look at a couple of simple problems. We're going to fly through these first couple because I'm hoping that y'all remember them, but we are going to work through them. So it says, how many moles of carbon dioxide is produced when 3.5 moles of octane combusts? So the very first thing that we should do anytime we're working with stoichiometry is we should write out our chemical equation. So I'm trying to combust octane. Well, what is octane? Remember, octane is C8H18. Oct would be 8. We know that for our hydrogen, it would be 2N plus 2. 2 times the number of carbon plus 2. So we get 16 plus 2 is 18. All right. Plus oxygen. Okay, because remember, anytime we've got combustion, we've got to have oxygen. And that's going to go to form CO2 and H2O. Then when we need to balance, we're going to end up needing a 2, a 25, a 16, and an 18 for our coefficients there. Okay, now those are very, very important because that's where we're going to find our mole to mole ratio. So here it says how many moles of carbon dioxide, so we're looking for carbon dioxide, is produced when 3.5 moles of octane combust. So we start with our known, so 3.5 moles of octane, C8H18. We drop it low, C8H18. And we do that so that we're canceling it out. Now, we do know there is a ratio between moles of octane and moles of carbon dioxide. And that ratio is 16 carbon dioxide for every 2 octane. So I'll take that, I'll plug that into my calculator because moles of carbon dioxide is what I'm looking for. And my answer will end up being 28 moles of CO2. Okay. All right, so moving on. Sorry, I forgot, accidentally erased that. So moving on here. Now we're going to do a mole to mass. So I have 6 moles of magnesium, and they're going to react with excess oxygen. Excess oxygen just means that we're not going to run out of oxygen. So that means we're going to run out of magnesium, right? In a synthesis reaction, what mass in grams of oxygen reacted? First thing, balance. Magnesium reacts with oxygen. Remember, oxygen is a diatomic element. To produce magnesium oxide, we'd go back in and balance. We would need a 2 here and a 2 right there. So let's solve this. We start with our known, so 6.0 moles of magnesium. Moles of magnesium is not what I'm looking for, so I drop it low. Cancel that out. We're going to go from moles of magnesium into, we're looking for oxygen. We're looking for the mass of oxygen. Remember, the only way to go from one substance into another is to use your mole to mole ratio. So moles of magnesium into moles of oxygen. There is 1 mole of oxygen for every 2 moles of magnesium. Moles of oxygen is not what I'm looking for, so I drop it low. Cancel that out. We're going to go from moles of oxygen into grams of oxygen. It does have a mass of 32.00 grams for every 1 mole. Grams is what I'm looking for, so I can go ahead and solve. 32 times 6 divided by 2 gives us 96 grams of O2. So then that would be my answer. All right, so I want y'all to go ahead, based off of what we just saw right there, I want y'all to solve this one. So pause your video, solve this one, and then we'll quickly go over it. All right, so here would be the work that we have for this problem. So first off, I would need to make sure that everything is balanced, make sure my equation is written. They've already done that for me, so we can go ahead and move on. So I have 5.38 grams of LiN3. We're going to drop that low, go from grams into moles using our molar mass. Then we're going to drop down moles of Li3 in, and we're going to go into moles of NH3. That is a 1-to-1 ratio. Then we're going to go from moles of NH3 into grams of NH3, and we're going to solve because grams of NH3 is what we're looking for. So we'd get 2.85 grams of NH3. All right? Okay, so moving on. The next part we're going to talk about is the limiting reagent. Now remember that the limiting reagent is going to be the thing that's going to determine how much product can be produced. Why? Because we're going to run out of it. It's the thing that limits how much we can make. So if you're given two amounts in stoichiometry and asked to figure out what is your limiting reactant, or it might say something like how much product would be formed, the easiest way to work the problem is to take this to solve through both of the stoichiometry problems and then take your smallest answer. Okay. So let's take a look at this. This is essentially what a limiting reactant would be. So I've got x plus 2y produces xy2. All right, so that's my balanced equation. So looking at this, I've got some circles, I've got some squares. My squares represent x, my circles represent y. My formula for that would be this thing over here on the far right. So circle, square, circle, and that would be what we have. So just in general, looking at this substance, I'm going to have to figure out what's going to be my limiting reactant. So I'm going to go ahead and just actually draw lines on the left side just so I can see how many of each thing I would need on the right side. So I'm going to connect these two because it's two circles and a square. I'm going to connect these two circles and a square, and I'm going to connect these two circles and a square. I've still got two circles left over. So when I redraw that, I should be sure to represent that. So circle, square, circle, circle, square, circle, circle, square, circle, and then we have two additional circles. So then this would be my final answer for this. Okay, looking at this, drawing in my boxes, I'm going to draw that resulting particles in the box. Okay, so what was my limiting reactant? Well, my limiting reactant was X, whatever mystery element X was. Okay, now that would be conceptually how we can recognize what a limiting reactant is. But let's actually solve some problems and see how to find our limiting reactants in a given formula. So it says how many moles of FeOH3 can be produced by allowing 1 mole of Fe2S3, 2 moles of H2O, and 3 moles of O2 to react. So we're looking at those three substances and we're trying to figure out how much of that FeOH3 can be produced. So I'm going to zoom in a little bit here. Very first thing that you should do is make sure your equation is balanced, make sure it's written out. But I have 1 mole of Fe2S3, and I'm solving for FeOH3. So I'm going to go from moles of Fe2S3 into moles of FeOH3. And that's going to be, there are 2 moles of Fe2S3 for every 4 moles of FeOH3. And then I'm going to solve that, and I'm going to find I have 2 moles of FeOH3. Now I'm going to need to do that again with each of those other substances. So I have 3 moles of O2. We're going to go moles of O2 into moles of FeOH3. That ratio would be 3 moles of O2 for every 4 moles of FeOH3. We solve that, we're going to end up with 4 moles of FeOH3. FeOH3. And then lastly, we've got our H2O. So I have 2 moles of H2O. Let's See if it'll let me. Nope, we're going to have to go from this side. 2 moles of H2O. We're going to go moles of H2O into moles of FeOH3. And we have a 4 to 6 ratio there. We solve for that. We're going to end up with 1.3 moles of FeOH3. So then what would be the most amount of product? How many moles of FeOH3 can I produce? 1.3 moles. Why? Because at that point, I'm going to run out of something. Okay, and so 1.3 moles of FeOH3 would be the total amount that I could produce, and my limiting reactant would be H2O. Okay? All right, moving on. So looking at this next problem, they want us to solve for the amount of excess reagent left over. So essentially, we're going to solve for our limiting reactant, and then after that, we're going to solve for our excess reactant. Okay, and solve for what would be left over. So we're going to end up subtracting. So let's actually dive on into that. The very first thing that I need to do, so I have 25 grams of hydrazine, which is N2H4, and 66 grams of hydrogen peroxide, H2O2. And they're going to react to produce nitrogen gas and water. How many grams of nitrogen are produced? How much excess reagent is left over at the end of the experiment? So the first thing I should do is write my balanced equation. I have N2H4 plus H2O2 produces N2 and H2O. Go back in and balance. We're going to need a 4 here. And not a 4, a 2 there. Two there. Okay? So now we've got our balanced chemical equation. So now let's go ahead and plug in our numbers and start solving this problem. So I have 25 grams of hydrazine into H4. I'm going to go from grams of hydrazine into moles of hydrazine. Again, we need to go into moles because moles is the only thing that I can go from one substance to another. So there is 32.052 grams of hydrazine for every 1 mole. That would be my molar mass. And then I'm going to go from moles of hydrazine into moles of nitrogen. Looking at my ratio, that is a 1-to-1 ratio. Then I go from moles of nitrogen into grams of nitrogen. There's 1 mole for every 28.02 grams. Solve that, we're going to end up with 22 grams of nitrogen. Then we come back. I have 66 grams of H2O2. We're going to go from grams of hydrogen peroxide into moles. It's 34.016 grams for every 1 mole. Then we go from moles of H2O2 into moles of N2. We're going to do that using our ratio. We're going to have 2 H2O2 for every 1 mole of N2. And then we go from moles of N2 into grams of N2. There's 28.02 grams for every 1 mole. I plug that into my calculator. I get 27 grams of N2. So how much could I produce? I could produce 22 grams of N2. The next question says how much excess reagent is left over at the end. So what I do is I'm going to come back and I'm going to actually use my limiting reactant right there. And I'm going to use that and solve for my excess reactant. So I have 25 grams of N2H4. We're going to go, I'm going to zoom in a little bit here. We're going to go from grams of N2H4 into moles of N2H4. There's 1 mole for every 32.052. Then we're going to go moles of N2H4 into moles of H2O2. And that ratio would be 2 of these for every one of these. And then last, we're going to go from moles of H2O2 into grams of H2O2. There's 1 mole for every 34.016. We plug that into our calculator and we will end up with 53 grams. Now, that is not my answer. That is telling me how much of this H2O2, how much of the hydrogen peroxide I will use in this reaction. And so now I know how much hydrogen peroxide I will use. I know that I had a total mass of 66 grams. So 66 grams of hydrogen peroxide minus how much I used, and that's going to tell me I had 13 grams of H2O2 left over. And so that would be my final answer to that. Okay, so I'm going to actually leave these next 2 problems for y'all to work on your own. I'm going to write the answers, write the work, and then you can double check your work after you have finished up. All right, so go ahead and pause your video and then we'll go over it. Okay, so here is what you should have gotten. So for that first example with the 17 grams of ammonia, we found that with the ammonia, we could produce 30 grams of nitrogen monoxide. And with the 32 grams of oxygen, we could produce 24 grams of nitrogen monoxide, which means the amount of mass that we could make with nitrogen monoxide is that 24 grams. Okay? Moving on. Now, this one is kind of a throwback to something you learned in previous chemistry. So first off, we would have to convert from moles into grams of moles of CH4 into grams of CCl4. Again, we do that using our mole-to-mole ratio and our molar mass. Once we do that, what we have solved for is our theoretical yield. Okay. Once I have my theoretical yield, then I can solve for percent yield, which remember percent yield is actual over theoretical. And so I'll have 83.5 over 153.81 times 100. 83.5 was from what they told us in the problem. So they actually obtained 83.5 grams of CCl4. Theoretically, they should have obtained 153.81 grams. So then my percent yield would be 54.3% yield. Okay? All right. Now, y'all, this is a good place to pause if you want a quick break. But come on back when you are ready, and we'll dive on into the stoichiometry of gases. All right. So now let's take a look at the stoichiometry of gases. Okay. Now for this, essentially what we're going to be doing is using stoichiometry and the gas laws that we know to solve our reaction problems. Okay. So for this, again, it's just general stoichiometry. One thing to recognize is that if I am at STP, remember standard temperature and pressure, then what we know is that I have 22.44 liters per 1 mole of a gas. Okay. And so when we're talking about our gas laws, we do need to recognize that if we're at STP, then we can solve for our volume using that 1 mole equals 22.4 liters. Okay. Now, do remember that STP is going to be at 0 degrees Celsius, which remember is 273 Kelvin, and at 1 atmosphere. Okay, so anytime you've got those conditions. Okay, so let's go ahead and solve this problem. So it says how many liters of N2 are required to produce 115 grams of NH3 at STP? So what I'm going to do is I'm going to actually solve for moles first, and then after I've got moles, I know that I can use that ratio of molar volume, so 22.4 liters per 1 mole, because I'm at STP. So I have 115 grams of NH3. I'm going to convert from grams of NH3 into moles of NH3. I have 1 mole for every 17.034 grams of NH3. And then I'm going to convert from moles of that into moles of N2, Now, how do I do that? Well, I'm going to need to know my reaction, right? So I have N2 plus H2 produces NH3. I'm going to need 2 of these and 3 of these. That would be my balanced chemical equation. So for every 2 NH3, I would have 1 N2. Then I could convert from moles of that into liters of N2. And there's 1 mole for every 22.4 liters. Okay. So we would end up with 75.6 liters of N2. And that would be my answer. Okay. So I want y'all to go ahead and work these next couple of problems. Now remember that you'll probably end up needing to use some gas laws. So PV equals nRT, or the combined gas law, P1 V1 over T1 equals P2 V2 over T2. But essentially, you're just solving through these like a generic, a normal stoichiometry problem, and you might have to use some gas laws to solve for one of your variables. All right, I'm going to answer them. I'll work them out for you, and then you can check your answers here in a second. But go ahead and pause your video and work through those practice problems. All right, so let's take a look at this. So I have, first off with this top one, I would first convert from grams of silver into moles of chlorine using my molar mass of silver and the mole to mole ratio. After I got that, I got 0.232 moles of chlorine gas. And then I would use that and plug that into my ideal gas equation. So remember, PV equals nRT. I rearranged it into V equals nRT over P, which means when I plug all my numbers in, I would end up with 5.81 liters of chlorine gas. Moving down here. Now, remember that your gas laws are going to solve for gases, right? So here it's asking for the mass of potassium chlorate. Potassium chlorate is a solid. So when we solve with our gas laws first, we're not going to be able to solve for that one. We're going to have to solve for a gas. So in this case, oxygen. So I have, again, PV equals nRT. I'm going to be solving for my number of moles. So N equals RT over PV. Plug that in, and I get 4.60 moles of oxygen gas. Again, I had to solve for oxygen because it is the only gas I have. Then I convert from moles of O2 into moles of KClO3, and then I convert from moles of that into grams of that. Solve it. I end up with 564. All right. So that would be it for that problem. I'm actually going to work this one with you because it does add one more thing to it, and that is talking about excess water. Now, remember, we know that water does exert some vapor pressure, and so we do need to take that into account a lot of times. So the question here, we have to take into account our partial pressure of water and subtract it out. So here I've got sodium, water, NaOH, and H2. That is already balanced for me. So the question says, when sodium reacts with excess water, how many grams of sodium are required to produce 6.50 liters of hydrogen gas over water at 30 degrees Celsius and a total pressure of 671.8 mmHg? Well, first off, we know that our solids are not going to exert, they're not going to exert a pressure. And so they don't have a pressure that we have to take into account. Our pressure is going to come from our gases, right? And sometimes the vapor pressure of a liquid. But in this case, the only liquid that we've got is water. And they told us that the vapor pressure is 31.8 mmHg, and our total pressure was 671.8 mmHg. So to solve for the pressure of the hydrogen gas, it's just 671.8, which is the total pressure, minus the pressure of the water, 31.8. And we're going to find we have a total of 640 mmHg for hydrogen gas. Well, now we've got our pressure. We've also been told our volume and our temperature. So we can use PV equals nRT to solve this problem. We're going to need to know the number of moles, though. So N equals RT over PV. And I plug my numbers in. So N equals 62.4. So that's going to be my ideal gas constant if we're in mmHg, times 303. Again, that's my temperature, so it's 30 degrees Celsius plus 273, which turns it into Kelvin, divided by the pressure, which we found was 640, times my volume, 6.50. I plug all that in, and I end up with 4.55 moles of H2. Now I can convert from moles of H2 into grams of sodium. So we'll go moles of H2 into moles of sodium. There's 1 mole of sodium for every 1 mole of H2. And then we go from moles of sodium into grams of sodium using our molar mass, which is 22.99 grams for every 1 mole. Plug that into my calculator, I end up with 105 grams of sodium. And that would be our answer. Now we're going to go ahead and move on to our solution stoichiometry. So this will be the last thing that we cover with stoichiometry. For this, again, you're basically just doing something similar to what you did with gas laws, where you're going to be incorporating that idea of molarity, right? So molarity equals moles of solute over liters of solution. So let's take a look at this first problem. It says 171 milliliters of 0.450 molar lead-2 nitrate reacts with a 2.25 molar lithium chloride solution. What volume in milliliters of lithium chloride is needed to react completely with the lead-2 nitrate? Okay, first thing we should do is we should always remember to write our formula. So for this, I've got lead-2 nitrate, so that's going to be PbNO3 2 plus lithium chloride produces PbCl2 and LiNO3. We would need to go back in and balance, which would be a 2 there and a 2 there. Okay, so now we're going to solve this problem. So the problem says, what volume of lithium chloride is needed to react completely with that lead-2 nitrate? So I have 171 milliliters of the lead-2 nitrate. And I'm going to use that as my starting point. Why? Because I know that I've got that much lead-2 nitrate, and I'm trying to figure out how much lithium chloride I will need. So I'm going to drop that low, go from milliliters of lead-2 nitrate into liters of lead-2 nitrate. Now, why would I need to do that? I would need to do that because molarity, remember, is moles per liter. So we got to get out of milliliters and into liters. There's 1,000 milliliters for every 1 liter. Then I'm going to drop down my liters of lead-2 nitrate. And we're going to use that to go into moles of lead-2 nitrate. And there is 0.450 moles for every 1 liter. Then we're going to go from moles of lead-2 nitrate into moles of lithium chloride using our mole-to-mole ratio. So there are 2 moles of lithium chloride for every 1 mole of lead-2 nitrate. We're going to keep on moving. I'm going to continue this down here. So I've got my 2 moles of lithium chloride. I'm going to drop that low, so moles of lithium chloride. And we're going to go into liters of lithium chloride using our molarity. So I have 2.25 moles for every 1 liter. And then liters of lithium chloride into milliliters of lithium chloride. We know that there's 1,000 milliliters for every 1 liter. We plug that all into our calculator, we will end up with 68.4 milliliters. Okay? All right. Well, that is it for the notes. I am going to leave the rest of it for practice for y'all. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.